and I would like to talk to you today about debugging Java out-of-memory errors when the heap is giving us troubles. Let me give you a rough overview of what I would like to talk to you about. We will begin with what motivated this talk. I will then remind you or tell you for the first time, depending, how you go about capturing a heap and how you go about analyzing it. We have both command-line tools and we have UI tools for doing that. I will then show you how to walk your heap using code. And then we will close out with a little discussion, and hopefully at that point, the rest of the pizza will have arrived and we can all go and take the discussion. So without further ado, I go to my motivation, and I first want a show of hands. Who all has spent at least a day debugging an out-of-memory error? All right, great. 3 days. Oh, nice. 5. A week? 2 weeks? 3 weeks? 1 month? More than a month? Okay. Yes, so that more than 1 month is me and my DevOps. We had a bug in our system where the connection library that we were using for holding SQL connections was stashing the pools on the thread local storage for caching purposes, which works really good if you're going against test databases that are created once and then destroyed and never come back. And so it really depended on the mix between how many tests we were running and how many production things we were doing, whether the system would crash after 3 days, after 5 days, after 7 days. So that motivated my interest in OOM. And it's in some sense still surprising that they happen so frequently in 2026, right? With microservice architectures, we have the kind of strategies that Rina was just talking about. We have resilient system designs and so on and so forth. And we're in cloud computing, right? You don't have enough RAM, you throw some more sense in it, and you get a bigger machine. And so we would think everything is fine, and it turns out this is only the case until it's not. And I argue that we will see these out-of-memory errors as long as time is still money. And one of our key performance indicators is that it has to be as responsive as possible, because that pushes us developers toward buying time with space, which means we start caching, which in turn means that we distort the liveliness that the garbage collector depends on for helping us out with the memory. And the brittleness of the KPIs begin to skew the incentives. The memory is global, and the cache is a local optimization that every developer has no incentive to take. And so therefore, bad caching, as in the example with the SQL connections that I began this talk with, will cause out-of-memory errors. Now, once we try to dig down into these, we find out that modern software caches are very complicated objects. They have interesting object graphs. They do all sorts of cool stuff. They work around concurrency. They support time to live. They have weighing functions that allow you to decide who gets evicted or who gets prefetched. So we had better bring good toolings to this problem if we want to deal with these complex objects. They're shiny machines. Once we go down under the hood, we start losing some of the things that we're accustomed to from our object-oriented programming days, right? There are, on a heap, there are no abstract classes, right? Everything is concrete. There are no more type parameters. Everything's erased away. But you have plenty of implementation classes, interior and hidden classes you didn't even know were there, and optimizations for classes. So I was not aware that hash map descends into a red-black tree if the number of elements is small enough. That was a bit of a surprise. What that does though mean is that if you use concrete classes and you don't just simply use the standard collections for everything, you're gaining some benefits because they're much easier to find in the heap. The other problem, of course, is that once you're under the hood, once you're in the heap, all secrets are revealed. Everything is now in plain text. Everybody can get at any private information, and you have configuration information just out for the view. So this will be a problem for when we try to tackle the issues. And then the third problem is that we have interrupted the garbage collector. Right? The garbage collector was trying to collect, it didn't succeed, it gave the error, and now we have a heap. There's a mix of live and dead objects that the garbage collector didn't get around to collecting or decided it wasn't worth collecting because they weren't going to help anyway. So therefore, when we use our tools, if it's not already default, we have to bring the live option to bear. We have to make sure they only show us the live objects. The other ones are sort of like artifacts of the process. And this is especially true if you're not actually the unlucky person debugging the garbage collector. So let me start you out on what you can do from the command line. The modern tool is jcommand. Back in my early days, it was jmap. I wrote a little example program for us. It doesn't do much. It's just the main function that takes a number of seconds and goes to sleep, so we can grab its heap. So how do we go about doing that? We call the JPS function to tell us what the processes are. We found our little snoozer program and its process code. And then we call the jcommand function. We pass the process ID to it, as well as the command for getting a class histogram. And that will tell us what are the classes that are allocated the most often and that are consume the most memory in descending order. So this is already very useful. How does the jcommand do that? The jcommand goes and it uses the JVM tool interface to talk to the snoozing program in this case, and obtains that information from it via the API call. This means that you cannot have a program dump its own heap without some extra help, because you freeze up the moment you try to do that. So we need this indirection of either Java Bean or the command line tool. In this particular case, we're not actually interested in our assumption in the entire heap histogram, so we are doing some eager filtering. Since the output of the tool is just a list, a text file, so to speak, we can grab over it and get out our pieces. But that has some disadvantages in the sense that if we later decide that this wasn't the group of collections or classes we were going to look at, then we've already lost this information. So therefore you want to be able to pickle the entire heap. For that you'll call this like the sister function, so to speak, gc heap dump. You use the, you want to compress this. This is going to be a huge file in many cases. You want to compress it aggressively. You may remember that the -9 option on gzip is best compression. And you also have to give an absolute path name. The reason you have to give an absolute path name is because it is going to be the JVM that writes to that location. So it has to be something that it can see, it can write to. Once we've pickled the current heap, we end up with an href file. That is for historical reasons, that is also gzip. It is even for a trivial program quite large, as I said. I gave you a heap, sort of an octal dump of the first couple of bytes of this, uncompressed. You can see there's a nice header there, and then comes the enumeration of the classes that were in the heap. So we not only have the ability to use command line tools to get heap dumps and heap histograms while we run, we also have the ability to tell the JVM that should it run out of memory, it needs to dump a heap. So there's two options for that. You have to turn on heap dump on out of memory. This is off by default. And then you have to heap dump and give a path that the JVM will be able to write to. I highly recommend you have something in there that distinguishes it, otherwise in production, your heaps are gonna write over each other. Unfortunately, the JVM cannot dump compress. That means you're going to get something that's about 1.3 times, 1.5 times roughly, as large as the heap that you specified. Since in production we like to run with large heaps, this is going to be a very big file. Because by definition, we just ran out of memory, so everything is going to be consumed. Right? And so a 16 gig heap is going to clock you in at around 20, 21 gigs of file. You're going to have to compress that and move it off later. As I said, the JVM can't help you there. And it's going to delay production. If you're dumping a heap that is in that order, you're going to have no place to run another instance for about 5 to 6 minutes, maybe. So you need to make sure that you have really fast disks there, local SSD if possible, because it's going to take you a while. And you're going to get pushback from your operation team. They're unhappy about the exact two things we talked about. First of all, they're not going to be interested in giving you a local SSD on that node just so you can capture a heap dump. Plus, whoever the security people are, they don't want their GPDR violating data in that heap dump sitting somewhere on a disk unencrypted. I did research for this talk and checked. There are some tools that post facto will walk over and erase the PII looking information in the heap. I'm not very excited about this plan. That made my debugging very hard. It's interesting that nobody has built a system that does encryption on the fly. I have some ideas on how you could do that. We can take that up during the discussions. So now we have a heap. What do? We are going to analyze it a little bit. Oh, left arm, too bad. We're going to analyze it with some visual tools. I'm switching my use case now. I'm using the popular Java bibliography database for doing big text type bibliographies, JabRef. And I'm going to use VisualVM, an open source project that's very popular for this. Lots of people like to use Eclipse Mat. I personally find the user interface confusing. I prefer VisualVM, but your mileage may vary. So if I boot up into VisualVM and I attach to my JabRef process, the first information I get is some basic information about the JVM, how it was configured. In the first orange box, you see the arguments, how it was started, what version of Java you're running, and so on and so forth. Most interestingly, it will also tell you whether dumping an OOM on OOM was actually enabled or disabled. This will tell you why. For example, in production, something didn't actually rate its own. In the top, there are 4 tabs. The monitor tab will allow you to press a button, say dump me the heap. I forgot to screenshot that. So we're going to fast forward to the part where we have the heap dump. And now we have a basic summary of the objects, right? This doesn't look all that interestingly different from the heap analysis from the histogram that we got earlier. But this is just the beginning. Now notice that this is still an empty bibliography database. There's not a single book or anything to find in it. We've already fried away about 70 meg. We're now going to load some literature into our bibliography database. And we're going to take a second heap dump. And the numbers have clicked up. We're going to look at that in a moment and compare them. And so we notice, for example, that some of the data objects, if you sort them by size, some of the object classes are now coming earlier. They are now dominating in ways that they were not before. They're not more hash tables. However, because the image is larger, the percentages all have gone down, big surprise. And notice also that even though I am pretty sure that this hash map with a mega of bytes is the exact same hash map it was in the other dump, the secondary numbers on there, so this is no longer 7017, but it's now 143. So just be advised that if you compare dumps against each other, these numbers are not stable. This just comes from when the dumper iterates over the heap. Let's drill down a little bit. We have in our little menu, we have 2 choices that are interesting. One of them goes for the objects view. The other one goes for the so-called OQL console, and we will drill down on that in just a bit. The basic object view looks exactly like the one in the heap histogram. However, the difference is now we have a UI. We can actually start to look into the objects themselves, which the view, of course, doesn't give you. So in this case, I've picked out 2 pieces of information that I wanted to draw your attention to. First of all, as I said, if you look at the string number 1179, that's Fox in orange, its text is clearly visible, right? If that had been a password, everybody would have it. The second one is the string number 1177. This is going to be our friend for the next couple of slides we're going to look at. So we're switching our focus to that string, and we're going to open it up. So you see 2 sections. The top part is the static fields of the class. It's actually a little bit of a screen real estate waste that they show that on every single object, because otherwise they all have the same static field. But it's sort of nice for the debugging, I guess. And then you have the actual references. And by references, they mean which memory pieces refer to this object. And that's where we can start walking down the rabbit hole to find out why is that string even still in our heap. And so we click down and we click down, and there's ever more references to the object, potentially. And one of them is the bad guy who's holding on to this object for us. And as we do this, we sort of begin to wonder, this is rather impressive that they so quickly can determine which things point to this. How do they do that? And of course, they have a back index. So the very first time that the tools load up the heap, they will compute a back index. This is perfectly fine if you do a small heap like I have in my example, which is 70 meg. You won't even notice it if you're pulling in a 21 gig heap file. This is a great moment to either get some pizza or some coffee. Now, as I said, we have to click through this, but sometimes we don't know which direction we're trying to click, and it would be nice if we could just have some code click for us. And that's what we're going to do next with the so-called OQL console. Let me briefly tell you, so OQL stands for Object Query Language. It's supposed to be an SQL dialect that allows you to query the heap if it was a database. I have to tell you personally, I find that part of the console completely unhelpful because I never have any of the questions that the documentation suggests you should try. I have very different questions, and so therefore I take advantage of the fact that this is a complete JavaScript interpreter. So you can write JavaScript functions to walk across the heap, and that's where the money comes in. So in this particular case, we're going to first solve the problem that if somewhere in the heap dump we see an object that we would like to get our hands on programmatically, for example, as the starting point of a search, then we need a way to say, I'm looking for the string that's called 1177. And this is what this little program does. You define the class, you say it's a Java string, you tell it which one you want to get, and it returns the object. And let me explain to you how this works. So in this particular case, the JavaScript function is called object_num. Ignore the part that I grayed out. This is just error checking on the arguments. It's a very versatile function. The real meat starts at heaps.objects. So heaps.objects is a function that returns you an iterator that will walk you over every instance of that class. The second argument is really important because it controls whether you get just the class that you specified or the top class and all of its subclasses. So depending on what you're debugging, this can turn out to be a real difference. And the third one, which I'm not using here at all, is a filter. If you don't specify, you get all of them back. If you have some more detailed information, you can try to filter on that. I have not found that useful, so in my example, we don't do that. Now, all you have to do is you're looking for string 1177, so you call that next on the iterator 1177 times, and lo and behold, guess where you are. At this point, we now have a way to get at any object we would like to get in the heap that we see in our visualization. So now we can say, let's assume for sake of argument, that we have a very strong suspicion about where this leak is coming from. So we're going to ignore all the references that are grayed out here, and we're going to focus on the event source. This is not a sort of a trivial, or this is an interesting example because event handlers are notorious for being the places where loitering references hide. Right? People register for the event, they never unregister, they pile up there in the dictionary. Okay, half the audience is nodding along with me. Thank you very much, I'm glad we agree. So how can we find this with minimal clicking? That is our mission in solving this programmatically. And of course, the answer is a mark and sweep algorithm. So we're doing with an object graph. This is not very surprising. Let me quickly split up the function for you. The top part is the GraphWalk setup. The bottom part is just the result formatting, and the middle is the actual search. Anybody a little bit shaky on graph and walk-in? Nah, we're all close, right? Okay. So what are we doing here? We're basically saying we're seeding our search space with the endpoint of the pin object, and then we use the refers function that our heap API gives us to give all of the pointers back that point to that, right? And we say, okay, we were told to look for event handler managers, so we're going to look at the name of the class of that pointer, the class of .name call, And if that is equal to the enclosing class, then we push it to one of the terminals, that our search has succeeded. Otherwise, this is a point that we still need to inspect, so we throw it on the to-do list. And because you can sometimes search deeply, you will see that I initialize max rounds to 10,000, and I've searched deeper than that, I will tell you that. You just have to keep sure that you keep counting along, just so that you don't run forever and never find out anything interesting. In this particular case, we're very lucky. The graph is sizable, but not that deep, right? We searched 300 objects. We walked 10 steps deep. We get a whole set of them back. That's because the code that I wrote doesn't know about the grayed out area. So it finds all of them, not just the one we're actually hunting for, but our event handler manager is the first one, so we get that one back. And so now we have basically saved ourselves the clicking through this internal user interface in finding exactly what it is that is pinning our data in place, and I think that is a clear win. That said, let me close out with a quick discussion. So the overarching story of this talk isn't necessarily how do I beat OQL over the head to give me the pointers that I want, right? We want to prevent the OOMs before they ever show up. Right? So if you need to architect memory, like you need to architect your other resources, you should monitor your caches globally. This is trickier than it sounds because it often interferes with the performance of the caches, but you need to figure out some way of doing that. You need to tie your key performance indicators back to the cache consumption so that your devs can't trade off the one for the other easily. Or you assign cache budgets to the teams. You get to cache so many things and that's all you get. Or you control the time to live. The more of these strategies that you have, the more difficult it becomes to easily bypass your KPIs, and it's going to pay off in the quality of your system. Failing that, however, you need to configure your heap dumps so that you get one when you run into OOM, if you can convince your DevOps people. You can use the J command histograms to monitor the suspicious states. It's much cheaper just to get the histogram. I wouldn't try this in peak times, but like 2 o'clock in the morning is usually a good time for that kind of stuff. You can then pull the stuff into VisualVM or Eclipse, compare the heaps, look at them, and if all else fails, you write some nice scripts for rummaging through the object graph, and now you have some things that you can check into Git, or into Gist at least, and you have some debugging tools that for your toolbox that you can share. The scripts I showed you today, I wrote in 2019 or something like that. So this really transfers nicely. And other than that, I just wish you good luck and stay out of trouble. If you want to get the slides and if you have any feedback for us, then please scan this QR code. We will take you to the website and we will tell you where to download the slides. If you have any questions, I will say a few and then we can move on to the next part of the network. Yes, sir.
Do you know if when I trigger the garbage, the heap dump, will it run the garbage collector immediately before it captures the dump?
There are switches for that. There's one that runs it before, and there's one that runs it right afterwards.
Okay.
You can always ignore them by turning on the alive check, which is sort of on by default. And so it's mostly going to control the size of the file you get. That's my understanding.
But does this also apply for the dump on OOM?
No, yeah. So that's an interesting point, right? So we're getting this OOM call by the garbage collector, right? The garbage collector just completed a cycle.
Yeah.
I didn't go into that in detail. I'm sorry. I will rush back and amend my error. Yeah. So there's 2 OOMs that the garbage collector throws, right? The first one is the Java heap space. So the GC ran and it failed to get up enough memory. right? The second one is the overhead limit exceeded. So 90% of the time that the machine was running your process was spent in garbage collecting, and you only got 2% heap improvement out of that. Clearly, these values are configurable, at least to some extent. But so in this situation, what that means though is that in most cases, the garbage collector was already in the middle of a GC. So a lot of the garbage was already gone, that it could easily find. Where it usually fails means that it found like a huge array that it has to transport. It couldn't allocate the space for the big object to do the transport, and it gave up.
Okay, that's why I still have that.
That's why you still have a few. Yeah, it was in some technical sense interrupted. If you get the GC overhead limit exceeded, I think your chances that the heap is okay are much higher. Right? But since there are switches for saying, oh, this is unreachable anyway, it's not that big a deal, actually. You just need to know that that possibility exists, right? So that you're not, I've also, not quite as long as the other one, but I spent like a day debugging why are these objects still there? They don't seem to be referenced by anything. Well, then because they're no longer live objects. Right? Yes. What can you do? Very good question. Thank you so much. Any other questions? Great. You've been an awesome audience. I appreciate it. And let's go network. Thank you.